All right, so guys, now again, in front of you, you should have the activity sheet that we've been working on. And in addition to that, you need note-taking materials. In order to help you continue to be organized, guys, I will always give you the topic for what we're doing for the day and the date. So guys, today is August 24th. I would strongly encourage you to keep your class notes bundled together in the class notes section of your binder, but then also keep them in chronological order, and then you'll have a sense of the flow of the class. So guys, the topic for your notes today is representing accuracy. The date today is the 24th. So guys, as you're getting settled, let me help you understand the way the day is going to unwind. So what we're going to do today is we're actually going to go back and we're going to start by looking at the activity that we didn't complete last time. And guys, what we're going to do is we're going to learn the information that we need to complete the right-hand two columns of that activity. But along the way, what we're going to do is we're going to talk about how accurate are the measurements that you made and how do we communicate that to the world. So guys, at the end of the day today, you are going to be developing a skill that you're going to be using for the rest of the year, and it builds on what we did last time. So guys, with that said, your notes are now titled, you've got the date on there, but guys, I'm going to actually escape out of this, and I'm going to go over to the activity sheet. Please, you also grab the activity sheet, and guys, let's dig into this a little bit. So you should now have this dude in front of you. And guys, what I'd like to do is I'd like to talk with you about what yours should look like. Now, as we talk about this, guys, please ask questions. Please make sure that you understand not just the numbers, but the significance of those numbers. And guys, make sure that yours are correct. And we'll talk more about what that means in a minute. But guys, please make changes and corrections as you need. But here's the deal. If you're making changes and corrections by just blindly writing down everything on the screen, you're not learning anything. So guys, let's talk. We're going to start at the very bottom of the page. At the very, very bottom of the page, there's a question that doesn't involve numbers and circles. It involves a concept. And guys, the question, if I may, the question says this: what determines if your measurements had circled digits or not? Guys, please answer that question in writing if you haven't done it yet. And I didn't expect you to. Guys, please answer that question. What determined if your measurements had circled digits or not? There's two important ideas there that you should be drawing on when you answer that question. If you've already answered it, sit tight for a second. If you haven't, please commit to an answer. What determined whether or not your answers had circled digits? So guys, please now explain your answer to the person sitting next to you and see if between the two of you, you can come up with a more complete answer. Chat with the person next to you. Clara, what's that? This is the only time you're going to do this today. I think you're okay. Yeah. So guys, finishing up the thought that you're currently talking about. So guys, let's gather together around this question and let's see what we can figure out. So Eliza, I heard you at the very tail end of this conversation mention a very important term that's central to this. And guys, understand I'm not in any way calling anybody out, but over here in this area, I heard a male voice use a term that should not be part of your actual conversation. So I don't know who it was. We'll talk about it in a minute. But what were you all talking about these circled digits? What's it all about?
I said if it was if you were calculating it on a calculator, analog calculator.
Okay, so let's talk about that. So when we say calculation, we're talking about actually putting numbers in a calculator and manipulate. So not measuring and not calculating. So you tied all these ideas together. So you said measuring, analog scale, and estimating. Did you guys all connect those ideas? When you're making a measurement on an analog scale, you are estimating. Now somebody, and guys again, forgive me, but somebody over here used the word rounding. Guys, understand that when you are estimating, that's the opposite of rounding. When we round, we take big numbers and make them smaller. When we estimate, we take small numbers and make them bigger. So if you use the word rounding in your answer, I think you may have meant estimating, but guys, those are not the same. So somewhere in your answer, you should have the idea about measuring, analog scales, and estimates. So please complete that answer so that you have something solid to build the rest of the day upon. And guys, please, as we go, ask questions if you need. Y'all okay? You got this all nailed down? All right. So guys, with that said, now turn your attention to the answers that we specifically wrote down in this activity. Now guys, here's the deal. Your answers are probably different than mine. You may not have got exactly 22.0 when you measured the temperature of the water with that digital thermometer. So this is what should be the same. You should have the same number of digits and you should have the same digit places circled. So if your numbers are different, don't change them. But if you're circling or your decimal places are different, fix it so long as you understand why you did it wrong. And if you don't, please ask. So let's go through them. Number one, you had a digital thermometer that measured the temperature of the water. It gave you tenths. You wrote them down. Then guys, on number two, you had a glass thermometer that was also in water. We learned that it's the same as the air temperature. But guys, that thermometer measured in whole degrees, so you estimated tenths, and then you circled those tenths because it was an estimate. Please ask questions if you need. Then guys, looking at numbers 3 and 4, you were simply weighing metals on balances. Those were both digital balances, and you had hundredths for your measurements, but they were not estimates because it was a digital scale. You okay? Mm-hmm. Yeah. And so if you got the units wrong, you're fine. Understand that we'll always use Celsius. And so, yeah, now you know, but you're okay. All right, so guys, moving along then. Number 5, you all should have got wrong. Do you have a number that's more in the range of 19? Yeah, guys, my bad. We bought new ring stands over the summer. I made up this key last year, and these are much more stout ring stands. They weigh almost twice as much as our old ones did. But again, guys, we're not concerned about the number. We care about the decimal and we care about the estimating. So maybe you have 19 point something on number 5, but that's just fine. We care about the decimal. We care about the circle. You okay? Okay, so questions through 5. All right. So then, guys, moving down, We'll go 6 through 11. Number 6, you probably have different as well. Frankly, that fault was mine. I put the wrong block on the triple beam balance. Instead of a piece of aluminum, I put a piece of steel on there. The block is the same size, but steel is more dense, so it weighs more. But guys, you probably got something on the order of like 126 or something like that. But again, the important bit is 2 decimal places, last digit circled. You okay? Okay. So then, guys, continuing along, a digital. Oh, yep. Okay. But I'll bet you can figure out, if you skip that as well, where we're at. So guys, continuing on then with the whistle, it was a digital stopwatch, no estimation, 2 decimal places. Now guys, 8 through 11. We're going to come back to this in a minute, but let's be clear about it now. Remember how these measurements were made. We went 8, 9, and 10. So when we made these measurements, we were measuring with a scale that had ever-increasing smaller units and therefore greater accuracy. So when you've made the first measurement, as close as you could get was to the ones place, 24. Then you were, 24. Then you were given the ones, so you estimated to the tenths, and we got something like 24.6. Then you were given the tenths, and so you estimated to the hundredths. Guys, understand that progression is an important concept, that we always estimate one place past the accuracy of the device. That takes us through 8, 9, and 10. Now, 11 is different, because when you did number 11, that was actually with a digital micrometer. It had a digital display, you were no longer estimating, and you wrote down all of the places that were represented, but no circle because there was no estimation. Guys, questions on 8 through 11, especially that idea of the scale dictating the decimals. You really okay? Okay. So then, guys, continuing and finishing this up then. So looking at 12 through 15, let me zoom differently. So on 12 and 13, you were measuring volumes with graduated cylinders. They measure in whole milliliters, so you estimated to tenths. Then oven cleaner, you measured with a digital pH scale, a digital pH meter. There are no units for pH, but we did write down all of the decimals. And then, guys, finally, number 15, you found the mass of water, a milliliter of water on a digital balance. You wrote down both of the decimal places, but there was no estimation because it was digital. So now, guys, we need to take a big, deep breath. What questions do you have about the rules for estimating, the way that we not only identify how many digits to estimate, but then also how those estimated digits become part of our recorded information and how that's different with a digital display? Things that you want to chat about. You guys okay? You're sure? You'll ask if you're not, right? Okay, so guys, understand this is going to be foundational to everything that we do for the rest of the year. When you go into lab next week, the expectation is that your brain can go digital scale, analog scale, how do I deal with those differently? When do I estimate? How do I estimate? And then where do units belong in my numbers? You're okay? Okay. Mindy, go ahead. It could have been different than yours. Here's the thing that we need to talk about. If you have a tenth estimated in that measurement, even if it's a different tenth than mine, you're just fine. Because remember, that's an estimated digit, therefore ours could be different. The thing you need to look for is, did you estimate to tenths and did you circle the digit? What else, y'all? You guys okay? All right. So guys, do this then. Keep this assignment in front of you, this activity in front of you. But guys, now bring your note sheet into view as well. And we're going to be bouncing back and forth between these two papers. So guys, I need to escape out of this. and I need to jump over to my notes stuff, and we're going to get started. Okay, so guys, this then becomes the transition. We have been talking, and you are now feeling more comfortable with this idea of intelligently making measurements based upon devices and estimation. Guys, today what we've got to do is establish some finalizing rules about how we're going to represent accuracy. So guys, first of all, let me explain to you what I mean by representing accuracy. Turn your attention to measurements 8, 9, and 10. Turn your attention to 8, 9, and 10. And guys, remember what we're looking at here is the length of a graduated cylinder. Now guys, here's the question that I have for you. Top, middle, or bottom? And I'm please going to ask you to vote. I know that this is awkward, but it helps me understand visually what's going on in your brains. Because I'm going to ask you to vote top, middle, or bottom. Of these three measurements, which one is more accurate? Which one are you more likely to trust? The top measurement, the middle measurement, or the bottom measurement? Please show me. Got there, here, there. Are you going sideways?
I'm going sideways.
You're going sideways. All right. We've got and another sideways. We've got a whole bunch of downs, and then we've got a sideways. So you have now become somebody that's not kind of an outlier, and that's awesome. So help me understand why you believe that middle measurement is more accurate.
Those tiny little lines estimating between them, it's just like trying to cut teeth. It doesn't really make sense, and you're getting some very different numbers.
Okay, so when you say the tiny little lines, you mean these dudes, right?
Absolutely, at the very top.
Okay, very cool. So
Between those, in terms of a single decimal, you're just going to get a bunch of different numbers.
Interesting. Absolutely, and I appreciate what you're saying, and I'm really glad we're talking about this. So, and I just totally forgot your name. TJ, thank you. Okay, so guys, relative to this idea, let's talk, because you bring up a compelling idea. Guys, understand that when we make estimates, there is inherently room in that for error, right? By definition, an estimate means something that could have error in it. The question is this: how can we limit that error? And so I understand that when we look at this, you have a better chance of estimating in between these marks than perhaps you do between these marks. But here's the trick. Understand that when we're using this scale, we can measure accurately down to a resolution that here we're having to estimate to. So while I agree with you that here it's harder to estimate, I would argue that by using this scale, we're not estimating to a level that we're required to estimate here. Do you buy the argument? So guys, then in conjunction with that idea, maybe we could all gather around the idea that this bottom number is most accurate. So how then do we know? Well guys, we know that it's most accurate, even with the limits of estimation. We know that this is the most accurate because it was made with the best scale. But what is it about these numbers that communicate that? And guys, the answer is the digits beyond the decimal place. So guys, here we estimated to ones, here we estimated to tenths, and here we estimated to hundredths. Because we're estimating to smaller pieces, we can trust that that number is more accurate. So guys, the big idea is this: the 4 and the 6 and the 8 are communicating accuracy based upon their location in the number. Guys, hold that thought. Location communicates accuracy. But this gets a little more complicated. If you want to scratch that idea down, you're welcome to do that, because we're talking about accuracy. And guys, that's an important idea. And if you don't understand that, feel free to scratch that in your notes. Location communicates accuracy. But it gets a little bit more muddled than this. And guys, I'd like to show you an example of how. So we understand that location communicates accuracy. But what about this? Guys, please don't write what you're about to see down, but join the thought. We should all now be comfortable with this idea. If we have 3 yellow sticks, if you will, and if we want to measure the lengths of these sticks, just like we did before, we need a scale. And so if I fly in this scale, we understand that the unit, and guys, again, this is stuff you're accountable for. If you can't do this, ask questions. Guys, the units for the scale are tens, so we estimate to ones. And this stick is not 9, and it's not 11, it's 10, so we write down the units, the measurement, as 10 centimeters. But now we've got a finer scale. On this scale, the units are ones, so we estimate to tenths. So it's not just 10, it's 10.0 because it's not a tenth above and it's not a tenth below. It's 10.0 with no tenths. But again here, TJ, we're looking at an even finer scale, right? And maybe this will bring out the error in your previous thinking. So the idea is this. When we look at this finer scale, now we're measuring accurately down to tenths. And so while I agree with you that it's a train wreck to try to estimate the tenths inside the tenths, now we can measure accurately to those tenths. So this is not just 10.0, it's 10.00 because now we're estimating down to hundredths and we just didn't find any. Does that process make sense in your brains? Because guys, this then becomes the important idea. And again, I'm going to ask you to vote with your thumbs. Guys, which one of these numbers, top, middle, or bottom, which one of these numbers is bigger? Trick question, right? Which one's bigger? They're all the same. It's 10 and 10 and 10. Guys, all of these numbers have the same numerical value. But here's the follow-up question. Which is most accurate? Top or middle or bottom? Do you see the connection? Are we all voting down? Guys, the bottom number is the most accurate measurement. And this is where this gets a little weird because now we have numbers that all have the same numerical value. Unlike 8, 9, and 10 in your activity sheet, guys, here 8, 9, and 10 had different values. Now these have all exactly the same values but not the same accuracy. The thing that's making this weird is the zeros. So now we need an all-encompassing set of rules that help us identify accuracy, whether they are different numbers or numbers with zeros. And this is where you're going to start taking notes. So guys, scratch this down with me. When we have this conversation, we are talking about what are called significant digits. So guys, really straightforward. What is it that makes a number significant? They communicate accuracy. So significant digits are digits that communicate accuracy. So here's the deal, guys. There are 4 rules, but you're only going to write down 3 of them because the 4th one is unnecessary. But you will never see, ever in this class, on a test or otherwise, write down the 4 significant digit rules. All you've got to be able to do is apply them. So guys, what I'm going to do is I'm going to bring them up on the screen one at a time. I would encourage you to write them down. Then some examples will come up, and you're welcome to write those down as well. And then at that point, we'll step through these one at a time. So guys, rule number 1 is this. Non-zeros communicate accuracy. Non-zeros are significant digits. So what do you need to be able to do with this? Well, guys, let me show you. You need to be able to take a measurement and you need to be able to identify how many digits of accuracy it contains. So if you'd like to write these down, you can. If not, that's fine too. So guys, if you had the measurement 96 grams, that number has 2 digits of accuracy because neither the 9 nor the 6 is a 0. Pretty straightforward, right? So guys, now what about this? If you have a number like 61.4, that number has 3 digits of accuracy because the 6 and the 1 and the 4 are not zeros. But now, guys, what about this? 0.52 kilograms. How many digits of accuracy? Well, we know that the 5 and the 2 are accurate because they're not zeros. But what about the 0? Well, guys, we don't know because we don't have any rules about zeros. So let me share with you the 0 rules, of which there are 2. Rule number 2, which is the first 0 rule, is this: final zeros after the decimal communicate accuracy. So guys, as you are writing this down, let me define these ideas for you if you're not clear. Final means at the end. If it's helpful for you to write the word end underneath final, that might be good. And then guys, after means to the right. So when we say final zeros after the decimal, we mean zeros that are at the end and to the right of the decimal. So guys, let me show you what we're talking about. So for example, this 10 centimeters. This might be worth writing down as an example. How many digits of accuracy is in 10? Well, we know the 1 counts because it's not a 0. But what about the 0? And it does not count. It is final in that it's at the end of the number, but it's not to the right of the decimal, so it does not count. So this would be 1 digit of accuracy. So guys, what about this? 11.0. Guys, this would be 3 digits of accuracy. That is a 0 that meets both of those criteria. It's final, meaning that it's at the end of the number, but it's also to the right of the decimal. It's telling us that we looked for tenths and didn't find any. So that's an example of a final 0 after the decimal, and that would then be 3 digits of accuracy. Yeah, please.
Why is the 0 and 10 not digits of accuracy? Because that is showing that you look for ones and you
Not necessarily. So for example, and I'm going to cheat a little bit, but if we have this, and imagine that whatever we're measuring is this long, it's not, but we're going to pretend, right? So the idea is this: when we're on a scale that can only measure by tens, we are not completely confident of anything more than the ones place. And so 10 in this example is actually really a measurement accurate to just the tens place because that's all we can say with certainty. So it's telling us that we're measuring with a scale, and actually we could even do it this way. This may drive it home even more. So now we have one that actually only measures in hundreds, and so if we put it here, we're like, that's about 10. We're estimating even to that place because we don't have more digits of accuracy to support a better measurement. Is that okay? Okay. So guys, other questions about this idea of zeros? Yeah, okay? So guys, let me show you some other examples then, and let's play with this to see where this takes us. So guys, imagine that we have this number. Imagine that we have the number 110. Is that 0 significant? It is not. It is final, but it's not after the decimal place. Therefore, it does not count. But guys, what if we add this? What if we add 0.110? Is that 0 significant? It is, because it's a final 0 after the decimal. So it's telling us that we looked for thousands but didn't find any. Now guys, what about this? What if we have a string of zeros that are final zeros after the decimal? And the answer is those all count. You can have strings of final zeros after the decimal, and they all count. So what questions do you have about this idea of final zeros after the decimal? Go ahead. Great question. Let's talk about it. So we know the 1 and the 1 and the 1 all count, right? But now these zeros are no longer final zeros after the decimal. So they don't count by that rule. But they actually will count in just a minute by the third rule. You want to just write it down now. Rule number 3, trapped zeros count. So those zeros are trapped by the ones that surround it. And those zeros count not because of rule number 2, but because of rule number 3 that says that trapped zeros count. So now, guys, let me throw you a curveball. What about this? What about 0.00200? Showing me fingers, how many significant digits? Is it 5? Is it 1? Is it 3? TJ's going 5. What you got there? Don't be nervous. It's only your future. All right. Don't vote with TJ. He's already proven himself wrong once. All right. So we got 5. What do you think, Anderson? You're going 5. We got 5. We got 5. So, guys, let's talk about this because it's actually not 5. And it can't be 6. There's only 5 digits. So, guys, let's talk. So, yes. So we know that the 2 counts, and then, guys, these are final zeros after the decimal, so those 3 digits count. Now, guys, check this out. These are not final zeros after the decimal. They are after the decimal, but they're not final. So, guys, let's talk about these zeros. If they're not significant, communicate accuracy, what are they? And the answer is they're placeholders. Guys, if we got rid of these zeros, the value of the number would change, but its accuracy would not. So those zeros are not significant. So this would only be 3. Questions now, please. Jason, right? Say that again. Oh, I see what you're saying. Hold on, let me make my way back to the board. So you're saying, here, let me get rid of that circle. It's kind of in the way. Okay, so you're saying, isn't this 0 trapped? So the question then becomes, trapped by what? And so we need, we haven't fully talked about it, so let's talk. When we say trapped, we mean trapped by other significant digits. So let me show you an example of when that would be true, and I think this will make more sense. Let's put a 3 right there. Now these zeros are trapped between the 3 and the 2, and now they do count. But the trapping happens by other significant digits. Is that okay? What else, y'all? These are great questions. Go ahead, Nick. No, you can have like these dudes are all trapped because they're between the 1. You can have strings of zeros. 6, exactly. So what if we had something like this then? What if we had 0, 0, 1, 0, 0, 1, 0, 0? So the 1s are significant. What about those? Trapped. What about those? Final zeros after the decimal. What about these? No. Do you see the distinction between final zeros after, trap zeros, and placeholding zeros? Guys, that's as difficult as this gets. You ready for rule number 4? Don't even write it down. Rule number 4 is simply nothing else counts. You don't need to write it down because all it is a stop. It says we're done. There's only 3 kinds of significant zeros. When you get to college and your university professors try to make this really difficult, which they will, because this is it. There are 3. They're non-zeros, final zeros after the decimal, and trap zeros. That's it. End of story. What questions do you have? You okay? Please, TJ. Not yet, because there's one more thing. You see that you're close, right? Because now we can identify the number of digits, but there's one more skill that we need before we move forward. So guys, there is one more thing that I need to share with you before we move forward. Well, there's one more thought, and then there's one more skill. So there is one more situation that you need to be able to deal with. So let me do this first. So are you guys all okay with rule number 3 that says trap zeros count? And then you're okay with rule number 4 that says no other zeros count? And then guys, if you would like, there's actually a website right here that has all sorts of practice on these if you would like to engage with that and just get some more practice if you need. Go ahead.
Estimated digits.
Good for you. Do estimated digits count? So let's answer that question by getting ourselves some estimated digits. So if we go over here and look at this assignment, which TJ is where your mind went, do estimated digits count? So let's look at this. Does the 2 count? The 3? The 8? Yes. Estimated digits are understood to be significant so long as they fit the 3 criteria. Yep. So guys, with that said, one other thought. So do not make the mistake right now of trying to be efficient and running ahead to try to get this activity done, because it's going to back up on you in a minute because you're going to miss this next idea. And guys, before we get to the last idea, we need to talk about this. What about numbers in scientific notation? I get the sense that some of you are good enough at math that what I'm about to share with you is going to be sort of an aha moment. But guys, let's talk about what you need to be able to do, and then let's talk about why. So, how many significant digits are in this number? And the answer is, don't worry about this and only look there. And why is that 0 significant? Because it's trapped. Now with that said, check this out. Guys, let's take this number and write it out. So if we write it out, we're going to move the decimal place 1, 2, 3 positions, and that number is 6010. How many significant digits are in that number when it's written out? 3. The 6, the 1, and the trap 0, and that is not. So guys, you ready for the big idea? When you put numbers in scientific notation, all you're doing is trapping the non-significant digits in an exponent. That's not an idea that you need to be able to talk about, but guys, that's really what you're doing. When you put a number in scientific notation, what you're doing is trapping the non-significant digits in an exponent and only representing the significant digits. But whether you understand that or not, what you need to understand is that when you're dealing with numbers in scientific notation, just look at the number, the 6.01, not the 10 to the third. Yeah. Yeah, understand you don't need to know it, right? This is bonus, but I'm happy. Okay, so the idea is when you put a number in scientific notation, you're trapping's a bad word. You're gathering the non-significant digits into an exponent. But again, that's not something you need to know. But that's what you're doing. Yeah, please. Yeah, because think about it. All you're doing is moving digit, but all of those zeros are not final zeros after the decimal. Yeah, so all of those zeros would be non-significant no matter how many there are. Just a second, go ahead. Yeah, great point. 6.10. And if you were to write, say it's 10 to the third, and if you were to write this out, you'd end up with this, which is only 2 significant digits, right? We're going to leverage that in homework today, because if we wanted to take if we wanted to take the number 6,100, and if we wanted to write that number to 3 significant digits, what we would do is put it in scientific notation, and it would be 6.10 times 10 to the third. So what you're going to find out is we can force zeros to be significant only sometimes by putting them in scientific notation, and you're going to see that in the homework today. Yeah. Guys, what else would you like to talk about? Okay, then we've got one more thing to do, and then you're going to have a productive rest of your day. And guys, it goes like this. Please write these 3 examples down the width of your page. including the numbers in parentheses. So guys, this is the bottom line. In order to be successful in the homework, in order to be successful with the activity that we're going to complete, you've got to be able to not just identify significant digits, you've got to be able to do what we're about to do together. So, here's the deal. These are the numbers that we're going to manipulate. These are the numbers of digits that we are going to round to. So guys, with that said, here's what I'd like you to do. Up above these numbers, please write down the number of significant digits in each of them. You should be able to do that now. If you can't, then you have identified something that you need more time with, and I'd love to help. So guys, let's do this together. The one on the left, 314712, none of those are zeros. That would be 6. Now, what about the zeros in that center number? Are they significant? And the answer is they are not. These are not final zeros. These are not final zeros after the decimal. They are not trapped zeros because there is not another significant digit over here to trap them. Those are not significant. So this would be 4. But now guys, what about the 0 in the third number? Why does that one count? Because it's trapped, and that gives us 4. So guys, let's pause again. Questions about those ideas? Okay, now we're going to round. So join me, y'all. Starting over here on the left, we are now going to round this number to 4 digits. So we go 1, 2, 3, and 4. And if it's helpful for you to draw these dots right now, go for it. But guys, you're going to be doing this all year, and you need to become proficient with this. So then guys, from there, we look at this next digit, and that is a 2, which rounds down, which means the 7 doesn't change. So we have 314.7. Now guys, some of you may remember the first day of class where we talked about the difference between rounding and removing digits. And you may remember that first day of class we said, when you are rounding numbers that are below the decimal, you do not replace the digits, you remove the digits. Do you now see why? Because guys, what if we did it wrong, and what if we replaced the 2 and the 1 with zeros? They're now significant zeros because they're final zeros after the decimal, and we're back to 6. So guys, the idea here is that instead of replacing the 2 and the 1, we remove the 2 and the 1, and now we're 4 digits. Questions there? Not when they're below the decimal. When we're below the decimal, we remove them. So let's look at another example. So guys, this we're going to round to 2 digits. There's 1 and there is 2. Then we look at the second 7 to figure out which direction to round. That tells us to round up. So we are going to end up with 0.0018. So Nick, what about this example? Do we replace the 7 and the 5 with zeros? You don't, because if we did, they'd be significant. Go ahead.
Oh, I was just going to say, so the 4 to 2 is that significant?
These are telling us what to round to. Yeah. Understand that at this point in the year, I just have to tell you, later in the year, it will be dictated by the calculations that we're doing. You good there? One more to go. So guys, it goes like this. We've got the 8 and we've got the 0. Those are our 2 digits. Now, what does the 9 tell us to do? Round up. So that would give us 8 and 1. But guys, now watch closely. What do we do with the 9 and the 2? Do we replace them with zeros? We do, because if we didn't, we're not rounding. We're taking the number 8,000 and making it into 81. So we do replace the 9 and the 2 with zeros. Those are not significant zeros, and that rounds to 2 places. Yes, ma'am?
What if instead of a 9 you had something like a 4?
Mm-hmm. Exactly. And so let's do that. So what if we had this? What if we had 8042? And we wanted, and this is coming right back to what you said earlier. If we've got this number, and if we went around that to 2, we've got 1 and we've got 2, but now the 4 rounds down. So that gives us 80 and then 00. But how many significant digits is that? Only 1. So how do we make this 0 significant? And the answer is we put it in scientific notation. So it would be 8.0 times 10 to the third. And now that 0 is significant, and we tricked it into being significant by putting it in scientific notation. How you doing, y'all? You okay? Okay, so guys, you've got 2 things that are due on Thursday. One of them is the homework assignment, and I'd like to show you how this works. So guys, please join me over here with this homework assignment. Not the activity, but the homework assignment, which is probably located now in your organized binder. Guys, first of all, this. As you allow yourself to page through this homework assignment, you'll notice that there are numbers written in Sharpie at the top of some of those pages. Those are the assignment numbers. This is 1. Notice that it's double-sided. Then 2. Notice that it's double-sided. And then 3, single-sided. Guys, what that means is in this unit, you're going to have 3 homework assignments. Today, we're only doing number 1. Notice that it is double-sided. Turn to the second side with me, please. On the back of this assignment, reading question number 2, it says, which students' data are the most precise? Please cross out that question. We are not going to do that question at this point in the year. We'll cover it later. Yep, just the second question. We will do it later, but don't do it now. So now, guys, turning to the front of the paper, let me get you started so you understand how this works. So guys, notice that you've got 2 sets of numbers. In this top set of numbers, you are going to identify the number of significant digits. So for example, 71 is 2. Now what about 5651.00, 4 or 6? Do those zeros count? Because they are final zeros after the decimal, that would be 6, and so on. Now, guys, join me at the bottom. Here's what you're going to do. You are going to bring these numbers mentally down. And for example, you're going to take 71 and you're going to round it to 1 significant digit. That would be the 7. The 1 gets replaced with a 0. That would be 70. Now you're going to take this number and round it to 2 digits. That would be the 5 and the 6. The 5 rounds up, so that means this would be 5,700, and so on. So you'll complete all of that, then you'll work on the back and you'll answer those questions on the back. In addition to that, now you are prepared to do the activity sheet completely. And so guys, let me show you what this is going to look like. Doing the activity sheet, what you're going to do, grabbing this, and I think it's self-explanatory, but let me make sure you're clear. So guys, it goes like this. For example, my first measurement is 22.0 degrees. That is 3 significant digits. Then in the next column it says round it to 1 fewer significant digits. Instead of 3, you're going to round it to 2. that would be 1 and 2, and the 0 rounds down, so that would be 22 degrees Celsius rounded to 2 digits. Then looking at the next one, 23.8 is 3 digits, rounding that to 2 digits, I would get 24 degrees Celsius, and so on. So guys, go ahead, Nick, what? No, you're always going one less. So for example, this is 4. So then you'll go to 3, and that would be, for mine, 27.9 grams. And does that make sense? Okay, so guys, this then is what you have for Thursday. You're going to finish this activity sheet. Should you get done with it, you're welcome to turn it in. It goes in the B2 lab basket over here. If you don't get done, do it before Thursday. Do at the beginning of class. In addition to that, you've got that homework assignment to do. It is also due the beginning of class on Thursday. Now guys, remember, all the answers to the homework are posted on our website, and I always put the answers at the front of the room. So as you're working on these, feel free to check your work. We now have about 15 minutes, so you may get done with all of this. You're welcome to work quietly with the person next to you. Please invite me over if you need more support. And guys, our goal today is to get as much of this done as we possibly can. So dig in, let me know if I can help. This is what we're doing for